Thank you for inviting me. It's always great to be in India and very nice to see these familiar places and this already familiar place. So I will talk about some work we did recently on clique recovery in random geometric graphs. With this call first. And I will start first with some motivation. So in general, like in the bigger context, this question is about recovery of hidden patterns in networks. Like today we heard a talk about counts in triangles, which we'll maybe try to hide from you. So sometimes you have some structures in the network which are atypical for that network. And that is what you want to find. So it actually, this problem actually has, in this context, a very long history. For example, already in the 90s, before network science became a big thing, this sociologist was trying to find structural holes in the network as like special kind of anomalous structure. Then in beginning of 2000s, when Google became really big, they were using PageRank algorithm for ranking web pages. And this PageRank algorithm depended on how many pages refer to a particular web page and what is the quality of those. And it was not that easy to cheat, but it was really possible to cheat. And many people created what was called link farms. They were like automatically generated web pages, which were all referring to each other and mainly to the main page. And by creating such link farm, you could boost your page rank artificially. So at that time was a big question of how to find these link farms, and Google were finding them and punishing them quite severely. Then, of course, there are network security, intrusion detection, and now more later fake reviews and followers, and blockchain fraud, etc. So these are all sort of different types of anomalies in networks. But of course, when we do math, we make all these anomalies much more well-defined and stylized. But this is a concept. So what is the Plancet-Clique problem? So suppose we have a graph and we choose at random k vertices in this graph. And then what we do, we say, okay, these are malicious vertices that are trying to create artificial malicious connections. So they all connect to each other. But everything we see is the adjacency matrix. So the question is, how can we find these vertices that created these artificial links? And this is how you can formulate it mathematically. You have n vertices. You select k vertices. These notations I will use throughout. And then the goal is to recover the clique with high probability. And then it's actually not a very easy problem. Yeah, okay, so first a little bit more motivation. In particular, this Plancet-Clique out of all anomalies can be anomaly of a certain kind. So there could be malicious connections, but it could be also some problem with the data, so that these connections are artifacts. But it is also a very interesting application that it could be a hinted message that is apparently in steganography is a problem of finding a hidden image in a hidden message in the text. Yeah, that is like it is a science of yeah, it's very hard to explain. I looked it up before my previous talk, but I didn't look it up before this talk. But it is basically analysis of this text and you find these stigos are the hidden messages in this text. I will look it up for you and I will tell you later. So okay, okay, going back to math, actually. Recovering this Plancet-Clique is officially not an easy problem, at least recovering it quickly, recovering it, say, in polynomial time. And this is a proof or like the story of the problem. So if you take Erdős-Rényi graph with n vertices and you connect each pair of vertices independently with probability 1/2, so your most standard Erdős-Rényi random graph, then if you look what is the largest clique in such graph, then it will be logarithmic in n, log n. Yeah, size log n. Well, log 2n, to be precise, this is a known result. However, If we want to recover a planted clique in a polynomial time, then the minimal size that we can recover is C times square root of n. And actually, when I just came to this conference, then I saw Vinay, and Vinay said, oh, look, this paper of ours appeared on arXiv today, and they were recovering a hidden clique in a hypergraph, and they discovered similar things. So basically, more or less like logarithmic to some power clique number, and you can recover a clique only of a size square root of n. And okay, for mathematicians and computer scientists, this is a huge difference, right? Okay, for many people, maybe they say, okay, what's the big deal? But if you have million vertices, then square root is 1000, and log 2 is, say, like 19. So that's a big difference. All right, so that is a huge gap. And now what we are trying to do in this work, we are trying to recover clique in geometric graph. And then the question is, can we do a better job? Will geometry help us to do a better job? So in geometric graph, we have vertices on the unit square. Well, actually, we look at unit torus, but it doesn't matter. And then we connect the vertices. We have really hard, like strict geometric random graph. We connect to vertices when there is a distance at most Rn. And then we select k vertices and connect all missing edges. And that will be our planted clique. This is drawn here. And our goal is to recover a clique with high probability by looking only at the adjacency matrix. So we do not know the locations of the vertices. We only know the adjacency matrix. So that is the problem formulation. And the question is, will it be easy? Like, you can imagine it will be easy, and it will be, you will see. So you may already believe that will be much easier. So that's it.
Question.
Yeah.
What do you mean by recover here? Can you?
Yeah, so that you have an algorithm that tells you this k vertices I click, and with high probability it's correct. That is what I mean. So, basically we only see adjacency matrix, but the fact that geometry exists should help us. I mean, even visually, you see this is a very strange construction, and we should be able to recover. And this is, then I will tell you how. All right, so why geometry we need? Well, geometry is fundamentally modeling this triangle closure. If two people know the same person, then these people also are likely to know each other. So in geometric random graphs, when three vertices are close, they are likely to create triangles. So that is a very natural model for triangle closure. But there are also other reasons why we want to study geometric graphs. Like this is a very famous one. This is a hyperbolic random graphs that is a model that started in 2010, greatly generalized since then, that can model both heterogeneity and a high number of triangles in real life networks by putting the vertices in hyperbolic geometry. And sometimes even if you don't have geometry, it makes sense to introduce it. So, and for that, we have graph embedding. So you can have a network and it doesn't have any coordinates. And yet sometimes it makes sense to embed these coordinates and to embed the vertices in multiple dimensional space. And it can be done in many different ways, but this is one of most famous algorithms, which is called node-to-vec, that uses basically random walk, streaks of random walks, and then they interpret the streaks of random walks as pieces of text. And then they use basically the off-shelf software that embeds language for embedding the vertices. So now our vertices are treated like words, let's say, in these long sentences that are created by random walk. So, and then they introduce geometry and show that a lot of problems such like clustering or also detection and ranking can be done good if you embed vertices in geometric space. So these coordinates are telling you something. So geometry is very natural in real life networks. Okay, so now this is what we are going to study. We will have n will be our parameter, and we will generate Poisson n number of vertices. These vertices will be put on d-dimensional torus, and we will connect to vertices if their distance at most Rn. And this will be our average degree, that is exact average degree, where phi d is the volume of unit ball in this d-dimensional space. And approximately, of course, the main term is this. And this is what we will denote by mu(n). So not exact average degree, but the main term. And then we select kn vertices and connect all the missing edges, and this will be our planted clique. And our goal is to recover this planted clique with high probability, so that the probability, again, answering your question, the probability that clique is recovered by our algorithm, so that we return k vertices and we say this is your clique and it is really a true clique, that probability has to go to 1 as n goes to infinity. I also would like to notice that problem is ill-posed when our graph is really dense, like the average degree is order n, and if our clique size is a constant, because in that case, any vertices can be connected with positive, like these k vertices can be connected with positive probability, so you will be no way of knowing whether it's planted or natural clique. So therefore, yeah?
So in the geometric setting, if two vertices are within Rn, they are anyway connected.
Yeah.
So the only edges you can add are more than Rn.
Yeah, but you don't know that because you don't know coordinates.
No, but you know Rn, right?
You don't know anything. You only know adjacency matrix, and you know the clique size. Yeah, so knowing the clique size is our assumption, which is maybe not great, but we at this moment assume that we know the clique size. Okay, so but we don't know the Rn and we don't know coordinates. We don't know anything about geometry. Okay, so now we will have parameter space, so we will make our mu dependent on n, and we will make our k dependent on n, and we will have a dense regime where mu will be order larger than logarithm. We will have connectivity regime where mu is of the order logarithm, and we have sparse regime when mu is of order much smaller than logarithm. And sometimes results will be different for these different regimes. All right. So now we are going to use two algorithms, and I will just tell you about these two algorithms one after another. And this is the simplest one, which also was the first one to be used for the Shreni graph. The state of the art for the Shreni graph is spectral method, but it gives the same order of size sort of clique recovery. So almost. Okay, so and that is basically based on the degrees. We say, okay, we add k artificial edges. So these artificial edges should increase the degrees of these k vertices, right? So if this k is so big that the vertices start having bigger degree than any natural vertex can have, then we have recovered our clique. That's basically it. And the algorithm is like this: compute all the degrees, return k highest degrees, and that will be your clique. Okay, so then informally, well, there is some proof and some work involved, but informally, very naturally, you can say, okay, if your clique size is bigger than maximum degree plus minimum degree, then you should be able to recover the clique, right? Because then all vertices of the clique will have degree higher than maximum natural. So, and that is more or less what our result is. But the way it looks is a little bit more complicated. This is not our result. This is from the book of Penrose, where he established actually what is the maximum degree in a geometric random graph and what is the minimal degree in geometric random graph. So this Tn is a maximal degree, and the small Tn is a minimal degree. And for example, you may notice here that when we have disconnected graph, so in this connectivity, in the regime where mu(n) divided by log n is smaller than 1, this is a regime where graph is disconnected. Then we have start having vertices of degree 0, and therefore minimal degree is 0 in this regime. So this is a known result, and now basically our result is very much aligned with that. It is simply maximum minus minimum. If Kn is bigger than maximum minus minimum, which is different, has different form in different regimes, then we can recover our clique. Yeah, so this proof is not very difficult, but this result is also not very sharp, because actually especially if clique is smaller or older than n, and usually it will be, right? Then you will not find the minimal degree vertex in a clique with high probability. So in fact, this minus minimal degree is an overstatement. In fact, we have to look for the minimal degree within a clique. And that is not, that turned out a little bit not so easy. So we have also, yeah, so this is basically what it is. Yeah, so let me see. So oops, sorry. So this turned out to be not so easy, and I will give you a negative result in a minute. So let me just reflect on this result. So this is more or less what theorem says. And the point is that, do we do better this way than for Erdős-Rényi? Well, if you look at the result, then we do better because we can recover, like, we can recover smaller cliques, but also if we look at the largest natural clique in the geometric graph, then it is of the order of maximal degree. So in fact, in geometric random graph, we can recover a hidden clique of the size of maximal degree. Remember in Erdős-Rényi, so the size of the clique number. In Erdős-Rényi, my biggest clique was logarithmic, but the smallest recovered clique was square root of n, right? Now, in geometric graph, the biggest clique is of the order max degree, and the smallest clique that we can recover is also now more or less of the order max degree. And sometimes even smaller, because in a dense regime, max degree and min degree are the same order of magnitude, so you can recover even tiny clique. Okay, so that means that in geometric random graph, we can do much better, and then in Erdős-Rényi, even with this simple algorithm. However, it's not our, how should I say, it's not credit doesn't go to us, but credit goes to geometry. Because in geometric random graphs, it is simply natural that vertices are close. So the clique that connected to close vertices, the degree also formed with your neighbors which are close by. And there it is easier to create a clique. And therefore, we basically, we can recover planted clique of the size of clique number. So there is no such order of magnitude gap, but it is only due to the properties of the graph itself. It's not because of the algorithm is smart or anything like that. Okay, so then, as I already started saying, that this condition is a little bit too strong. So what we really need is that minimum degree inside the planted clique is greater than maximum degree outside of the planted clique. That is what we want. Well, outside of planted clique is smaller than n. That will likely to be max degree itself, so that is easy. But that turned out a little bit difficult. So what is minimal degree of all vertices inside the clique? And the degrees of vertices inside the clique are not exactly independent. And then we also add kn to them. So that was a little bit of a hassle. So at the end, this is our negative result. I think it can be made stronger. But here we can establish that this vertex degree algorithm fails to recover planted clique with high probability when kn is smaller basically than maximum minus average. So if you, because in the clique, very likely you will have vertices with degrees slightly above average. So if your kn is smaller order than maximum minus average, then you can recover this clique. That is in connectivity regime, and in dense regime, you cannot recover a clique of the size smaller than square root of n, square root of mu. Okay, so this is vertex degree algorithm, and this is a diagram. So this is the mu, the average degree, and this is the k, the size of the planted clique. And this green area is where we know we can recover. Here in this red area, we know we cannot recover, and still there are some unknown areas due to this imprecision, because it's hard to characterize very precisely the minimal degree of the clique. And here is regime change, but very peaceful one. Simply with gray, we depicted the area where you can go, for example, from O of 1 to logarithm, etc. Because it is hard to, it's not a continuous diagram. It really depends on this, how it scales. Okay, so far so good. Now the next algorithm, which works even better. So this is a common neighbor algorithm, and this is what it does. So this algorithm, we go through, not through all vertices, but we go through all edges. And for all edges, we look at their common neighbors. And if they have exactly k minus 2 common neighbors, then, and if all common neighbors are connected to each other, then we say, okay, we found the planet clique. So exactly k minus 2 common neighbors and this k minus 2 common neighbors are connected. Then we found it. Okay, so this is the situation. These are connected to two vertices. Their maximum distance are from each other. And this is where their common neighbors may lie. And we discover planet clique if we find like something unnatural happening here. All right, so when does this algorithm fail? So there are, we found like 3 possibilities for the algorithm to fail. First possibility is this. Suppose we have a planet clique, and they have, of course, k minus 2 common neighbors, but they may also have a natural common neighbor. And if they have a natural common neighbor, which is outside from the clique, then it will be common neighbor number k minus 1. And then we cannot find them because we are looking for exactly k minus 2. Okay, so this is the first one. And the second possibility is that we find a pair ij such that one of them maybe is in the clique, but the other one definitely not. At least one of them not in the clique. And they have common neighbors who are all connected to each other. This is value b1 and exactly k minus 1 in total, which is value b2. And then our algorithm fails if either A happens and so either A happens or B1 and B2 happen together. And therefore, our probability of failure can be bounded by probability of failure A plus the minimum of these 2 probabilities. And now if we can prove that this probability goes to 0, then we are done. All right, so now failure A is very easy because this just means that we have one vertex which is very close to all clique vertices. And that means that all clique vertices are also very close to each other. And that is very unlikely, right? So this is more or less the scheme. So these vertices, like they have common neighbors, so their maximal distance is 2 times Rn. And basically all k minus 1 vertices have to be, like k minus 1 vertices have to be there around 1. So if you have one clique vertex and the rest k minus 1 have to be around. And this goes to 0 basically most of the time. The 2 to the power d is a constant. Mu over n will go, mu over n will go to 0. Then it definitely goes to 0. And if mu over n doesn't go to 0, then k has to go to infinity because otherwise it's just a trivial case and ill-posed problems. So for all problems which are not ill-posed, event A cannot happen. Okay, so then we are left with failure B1 and B2. And the biggest contribution goes from failure B1. So basically, it is very unlikely that 2 vertices will have common neighbors, which all will form a clique. And why is it unlikely? Because these are the 2 areas where common neighbors can live. And these 2 areas, the vertices in these 2 areas will not be connected. So then it will not be a clique. So to create a clique, these 2 vertices must have all common neighbors here. But if your average degree goes to infinity, that will be quite unlikely to have all your common neighbors here and no common neighbor in these 2 gray areas. And because of that, we can bound the probability of this failure B1. So, well, we have to consider here different scenarios because, you know, for dense geometric graph and for not dense geometric graph where average degree is smaller order of n, there are 2 different techniques how you do it. So when your graph is dense, then you have to do a tessellation of the space and to make these little pieces independent of each other and consider all these little squares separately. And if you don't have it, then it is, if you don't have a dense graph, then it is much easier. You can simply use like some union bounds. That is fine. And for dense graph, it wouldn't work. Okay, so then here we could found this probability, bound this probability of failure B1 by this big formula. But importantly, you can see here, this is mu n, this is a union bound. So mu n comes from union bound. And this is coming from this probability of having this place is empty. And this is a negative part. And the rest, this is like a smaller part, and the rest is a positive part. So this must go to 0. And that mostly will, but this regime will become then difficult. So for small mu, that will not happen. So for small mu, failure B1 may actually occur. So it means that if you have average number of vertices of the order this or smaller, then you can find a pair with positive probability where these two areas will be empty. And then their neighbors will create a clique. Okay, so for the dense regime, the bound, which will always go to 0. In the dense regime, it's impossible to have a pair with these two areas empty. All right, so but then, okay, but will in this difficult regime, will maybe failure B1, B2 help us? Okay, let's see. So, oh, this should be B2. My apologies, this is a typo. So this failure B2 and this should be B2 as well. So for B2, you see the failure B2 happens when the vertices have these two vertices, one maybe inside, but one definitely outside of the Planted clique have k minus 2 common neighbors, right? Exactly k minus 2. So in most regime, you can approximate the number of common neighbors with this Poisson distribution. And basically, the question is like where this Poisson probability will be highest and what parameter it will have. So the parameter will be different depending on what exactly is the relation between k and mu. And we have 3 different cases when this constant is basically this number of vertices in this area divided by mu. Okay, so so this is some constant between 0 and 1. So if k is smaller than that, then we have 1 lambda. If k is between these two, it will have this lambda. And if k is greater than mu, then lambda will be equal to mu. And that will be the formula. And the most difficult regime is this one. When k is between these two, then the bound is such that the probability of B2 doesn't go to 0. So then we identified the difficult scenarios. And now we can summarize. So basically, what is the probability that this algorithm will fail? Well, A is basically impossible. And B1 can happen, but for reasonably small mu. And then B2 will help unless mu is very close to K. Yeah? And you can see this in this diagram. Like, first of all, it is much greener than the previous one, as you can see. But also, like, this is again regime change. But also, you see, it's exactly what I said. This is where B1 happens, that it is possible that common neighbors will create a clique. And then it narrows down, and this is where K is equal to mu, or K is close to mu. In these boundaries, this is where we don't know. And why we say we don't know? Because it is an upper bound. So we know that our upper bound doesn't go to 0 here, but maybe it was just a very bad upper bound. Maybe now some of you say, oh, I know much better upper bound, and we will remove all this completely. Maybe it works everywhere. I don't know. Okay, but interestingly, and it was very surprising for us, if you look at here, like this area, known area is very small, and then it is green, 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 even for very small clique size. So actually for clique size 2, so we actually can recover a Planted age, which is very, we didn't expect it. So this is how it looks. But if you look at it, it's actually natural, because if your graph is like reasonably dense and you have 2 vertices and they have no common neighbors, that is strange, right? So k minus 2 is 0, no common neighbors. So that is strange. And that's why we can recover Planck H. And I really wanted to give you some nice illustration of this situation. I thought, what kind of real life situation can I come up with? And I don't know, who has watched Hitchcock movie Stranger in the Train? Nobody? Stranger in the Train? Okay, I'm telling you a story then. So okay, it's a very famous thriller of Hitchcock in 50s. Frank, yes, why don't you raise your hand?
You were looking at the side.
Oh, you raise your hand.
No, I didn't.
Fantastic. Okay, okay, so
Movie, everybody saw it.
exactly, everyone should see it, right, Frank? Yeah, yeah. So it's a thriller. So, but okay, I will not give you too many spoilers. But basically, two guys meet on a train in the 50s, and one complains about his wife, and another one complains about his father. And then they decided to swap the murders. So I will murder your wife, and you will murder my father, and nobody will suspect us because we both will have an alibi, and because we are total strangers, right? So I asked ChatGPT to make an illustration of that, and here's what I get. So these are the two guys and completely disconnected networks. So they're in different geometrically different part of the graphs. But this is Planck H that created malicious connection. And if only Hitchcock had an adjacency matrix, or detective who studied, if only they had an adjacency matrix with our common neighbor algorithm, they would immediately discover who are the culprits here. Where is the malicious connection? Okay, so do you like it? Good, I'm happy. Okay, so this again, the comparison between two algorithms. Well, maybe I should put this title, there is no free lunch, because of course, this is much better, but it has much higher complexity. So here complexity is n, here complexity is number of edges. So that is higher complexity. But common neighbor algorithm works quite well, and we can recover almost any Planck clique almost of any size. And here are some experimental results. You also see this as a result. This is K, the Planck clique size, and our n is 10,000 in this case, and we did it for different mu's. So this is mu is 1, and this is percent of cases when we could recover the Planck clique with vertex degree and with common neighbors. And you see that common neighbors always already starts out much higher and keeps higher, and after very like at logarithm, it already recovers everything. Here, even better results with more dense graphs, but what you see is here, and where is this happening? Where mu is close to K. So it is I think we can find, maybe one can find much better upper bounds for our probabilities, but I think there is generally regime where like the negative regime where you cannot, impossibility regime, where you cannot recover this Planck clique. And for that, K should be close to mu. Okay, and not close to mu, but slightly smaller than mu. And then again, this one, and again, we see a little bit this down. So, but here you see how well it works already for Planck H, and then becomes a little bit worse, and then it recovers again. So these are our results, and to be honest, this is like this is our first work in this direction. I hope that this direction is actually promising. So I hope maybe to do more on this. And the first conclusions, of course, geometry really helps. Even if you don't know geometry, the fact that geometry exists really helps you to recover. Recovery in geometric graph works so much better than in Erdős-Rényi. But second, our model was very strict. But I believe it will work for geometric graphs, more general geometric graphs as well. Like I think for hyperbolic random graphs, it will work as well with some modifications, maybe some other bounds. But even this polynomials algorithm should work. And maybe we can consider other subgraphs rather than cliques and other patterns. So this whole anomaly detection and hidden pattern detection in graphs, I think, is a very interesting topic that probably we will see many more talks about it in conferences like that in the future. And I'm even early in time. Oh, okay, fine. But maybe you are happy with shorter talk after lunch. So I will stop here. Thank you very much. And I will be happy to take questions.
So we welcome questions.
Is there an implicit assumption that the adversary who's launching the clique doesn't know the graph or the geometry or anything? So your long edge, which you used as an illustration.
Yeah, it's a very good question because yes, it is true that the adversary is not trying to hide. So they just pick two random vertices and connect. But if if adversary will try to hide the clique, for example, adversary knows geometry or adversary knows adjacency matrix, that could be made harder. Yeah, that is a very good question.
Yeah, thanks for the nice talk. So the clique number was order of the max degree, right? The clique number was of the order of the max degree.
Yeah, yeah.
And so you should be, I mean, there is always an algorithm where you can scan all the vertices and then you will be able to find the clique.
Yes, but in general, this is indeed like naively, you can do it in Erdős-Rényi as well, right?
Yeah, yeah. So,
but it's not a polynomial time algorithm, right? If your clique is not a polynomial size, if your clique is not a finite size.
Yeah, but the cliques number being of order of the max degree hints at there being no gap, the statistical computational gap.
Yeah, that's true.
Then this algorithm should work in some sense to recover the clique.
You mean the algorithm that just finds maximal clique in the graph? No, I don't understand.
It scans. Okay, maybe it's not. Yeah, I mean, as I mentioned, it's not.
So you see, the clique size can be does need to be fixed size. It can be, for example, logarithm size. Officially, well, a logarithm, of course, is not a very fast-growing function, but officially it is going to infinity, right? So, if you want a polynomial time algorithm, then n to the power log n is not polynomial. And you want, like, our algorithm at this moment is like a vertex degree is order n, and the common neighbors is at most n squared, usually smaller, the number of edges, basically. So these both are polynomial time algorithms. And even spectral method is polynomial time, because you can compute or approximate the spectrum in polynomial time. But for Erdős-Rényi, for example, there is no polynomial time algorithm that can discover a clique greater than logarithmic. Yeah. So and here is the same. Here is exactly the same story. So doing this scanning is not logarithmic. I think, by the way, that if we do some merge between the two algorithms, we probably can do it even better. We just analyze this kind of very basic forms.
Also, I would actually say that the common neighbors algorithm is actually linear time algorithm because your input is your adjacency matrix, which has n times mu n kind of entries.
Well, it is exactly this n times mu n. So it's a number. It's the order of the number of edges, right? So because you look at every edge, you scan all the edges, and then it can be more than n squared, but it can be more than linear because the network does need to be sparse. Sparse regime we have, like we cover all regimes, but it does need to be sparse. It can be even dense. We cover dense regime as well. Only it needs different analysis, but it comes down to the same.
So this common neighbors algorithm works really well. Just out of curiosity, what would happen if you would apply it to GN half? It can't break the square root of n barrier, right?
No, I do not think so, to be honest.
So most pairs basically have order n
Okay.
neighbors or something like that, right?
So common neighbors and Erdős-Rényi, yeah, it could be because you scan the edges, right, and then you look at the common neighbors, and the clique will have unusually many common neighbors. I'm not sure it will work in Erdős-Rényi 1/2 as they studied it. Yeah, no. Exactly. No, it won't. It won't.
Where it breaks, why it breaks.
Okay. Yeah, so now I have time for questions. Yeah, so yeah, exactly. Yeah. Where it breaks. So here, of course, geometry was very important because of event A, for example. Event A is basically impossible in a geometric random graph. It might be much more likely in Erdős-Rényi. I think this is where it might break.
The thing is that your geometry is very important,
Yeah.
and at the same time, you don't observe.
Yeah, isn't it? Yeah. It's also, you know, but we also, when we were deriving these results and it was also not very straightforward, and we started vertex, we actually struggled quite a lot with vertex degree because the idea was very simple. Maximum should be smaller than minimum plus k, for example. But it's very difficult because you have to take minimum in the clique, maximum outside the clique, and there is some dependency going on. So somehow we even didn't get the result as clean as we wanted to. We had the result initially with all sorts of inverse Poisson approximation, Lambert functions, and whatnot. At the end, we just threw it all away and said, okay, you know what? We just stick to the cleanest bound because we can't improve it by much. So it is surprisingly more difficult than it sounds. But then common neighbor is so much also better, and also common neighbors actually uses geometry. That's the thing, and especially in A. I think if you look at event B1, B2, Erdős-Rényi would have comparable probably performance, but A might break in without geometry because they cannot be all close. Yeah, so and I am actually very curious what will happen when geometry fails. Like if you have not such a strict restriction, but when you can connect far away but with small probability. I think this is also computable even with similar methods. We just didn't do it yet.
Okay, so if there are no further questions, let's thank Nelly again.
Thank you very much.